Hi, my name is Austin Carlson, and today I'll be presenting quantification of polymerization and backbone disruption in polydiacetylene-based spray-on sensors. You're probably going to ask, what are those and why should I care? Polydiacetylene is an organic polymer containing elongated pi systems resulting in color shift in UV light. That means that you take these building block molecules that you see right here, and in the presence of UV light, whenever they're next to each other, these triple bonds will cause radical reactions, resulting in elongated polymers with conjugated backbones, resulting in UV shift under UV light. So whenever you shine a UV light at it, it's going to basically shift invisible color spectrum. This elongated chain results in the possibility for stimuli to disrupt them, though, which here in the demonstration, you can see that after these polydiacetylene based sensors have been activated, they turn a blue color, activated meaning under the UV lamp for some period of time. Up here you can see different concentrations under different periods of time, and then you can see their response to heat here on the right. Here they're heated all the way up to 250 degrees Celsius, although they change to different colors depending on the extent to which they're heated. So at 200 degrees Celsius, they're a different color. At 160, they're a different color. However, much of the research on polydiacetylene-based sensors are in their liquid phase, in which they form vesicles like you can see here, due to these R groups right here, most often being hydrocarbons. So they form these kind of phospholipid-like vesicles, which is where much of the research on them has been done in terms of their color shifting properties. However, whenever they're sprayed onto a surface, you can still have the, as you can see down here, effects of the stimuli change in color. So theoretically, one could incorporate this into a wearable sensor, which could improve workplace safety. It improve our overall understanding of how wearable sensors can be used, and overall, it just improves our understanding of sensors in general. Like I was saying earlier, here's some demonstration of the current experiments. Here above is different concentrations, all activated under UV lamp for 10 seconds, and down here is after different filter paper materials have been UV lamp for the same amount of time, their shift to the red color after being heated at 250 degrees Celsius. However, with a color shifting sensor, one might ask the question, how do you quantify that? And so most often colors are split into different values in color space. An extremely common way is the Scilab color space, which was developed in 1976, and it splits colors into their brightness, green versus red hues, and blue versus yellow hues. But in the terms of our different systems here, both in UV activation and heat response, our color shifting results in spirals, which before, for experiments done with the response to different stimuli, they produced linear curves in the Scilab space. So Euclidean distance was used to model the progress of the sensor. However, that was no longer valid. So we set out to develop a system to accurately model the progress of these sensors and see if we could obtain any sort of insights from that. So we developed a way to model. Here you can see the figures on the right, the data versus the stimulations, the UV activation. And next we look forward to modeling the heat activation, so that way we can have both a idea of how concentration affects UV activation, and then how both concentration and the UV time affect the heat response to tune these sensors to specific bands. Here you see how the model changes as an effect of concentration, and so that this kind of valley right here is where it would be most sensitive. So like I said, in the future, we hope to just get a better understanding of the sensors